Okay, cool. Okay, so game plan today is we're going to talk about linear regression. As we'll see, linear regression is a way of characterizing a relationship between two variables with a line. Linear just means it's a line. So what we're going to talk about. We're going to talk about this. I'm presenting this from a very just like visual perspective. There's a ton of math. There's a ton of statistics. There's a ton of like linear algebra and calculus that's behind all of this. We are not talking about a single piece of that. I think it's super important, but it's not important. I think this stuff is also important. I don't think this is dumbing it down. I think this is presenting it in a different way that even if you know the math super well, at least in my view, like personally, I find that going over this, the visual intuition here is super helpful. So we are doing it that way. So we're going to talk about what this all looks like visually. We're also going to try to apply that to like interpreting regression tables that you'll see in like just about any quantitative social science paper. It might not be a regression like the ones we're doing today, but it'll be some type of statistical test that'll probably be pretty similar. What we're not going to talk about, lots of stuff. Like I said, this can all be presented very formally. If you take, have you taken Stats 250?
Next semester.
Next semester, okay. So this might be in Stats 250, I'm not sure. It will be very different from what I'm going to go out on a limb and say this is a cooler way to talk about it than the Stats 250 way. But I'm biased. So yeah, you can present this a lot more formally. And this is just a different way of thinking about it.
Wait, for calculus and linear algebra, is that for linear regressions too?
Mm-hmm. Yep. So what we're not going to talk, another thing we're not going to talk about is causality. So you may have heard the phrase like correlation is not causation. So if I see a bunch of people with umbrellas outside in the diag, that correlates with the likelihood that it's raining outside. When I see more umbrellas, it's more likely that it's raining outside, right? Those are two variables that kind of move in the same way. You could also think about, it doesn't have to be that they move in the same way. They could also move in other directions. You could think about a negative correlation where it's like the more like shorts and t-shirts I see in the diag, like the less likely it is that it's snowing. Like those are two that are going to move in the other direction. But the key is that those two variables are moving together. But like obviously that's not, the number of umbrellas is not causing it to rain, right? So just because two variables are moving together doesn't mean that one is causing the other. So you can use these tools to do like test causal things. And lots of the time what we're interested in is causal questions. What's the effect of the election of a new governor on turnover, right? That's a causal question. I'm saying there that like when you elect a new governor, that's causing people to reassess their job situation, or it's causing people to get fired, et cetera. But testing that's like super hard and involves a lot of assumptions that exist outside of the framework that we're going to talk about today. So, and there'll be more examples of why this is not causality as we go through. So I'm not going to talk about regressions in R. As I said, the next video will be about doing this in R. Last thing here is that this is one of so many different ways of characterizing relationships between variables. This one is like the workhorse that you see all the time, and is like a stepping stone to a lot more complex ones. But it's just to say this is not the end all be all by any means. Okay, questions out there so far?
Are we gonna look at the other ones soon?
Not now. We definitely will as we are like reading more stuff on bureaucracies, and maybe we ourselves will be doing other stuff when we like are actually writing something up together. But like for right now, we're just sticking with this. All right, so let's start with a question. And that question is, what's the relationship between a county's median income and its support for Donald Trump in 2016? So what does this look like? So on the vertical axis is Trump's share of the county's vote. And on the horizontal axis is the county's median income. So top left is going to be a lot of counties that are have relatively low incomes and were highly supportive of Donald Trump. Over here, we have like very democratic, very liberal, wealthy counties. This is like outside of San Francisco. This is the Northern Virginia, Maryland, DMV area, stuff like that. New York City. Washington County, very liberal, not like the wealthiest county out there, but also like definitely above the vast majority in terms of like wealth levels. So this is just like the visual relationship here between median income and Trump's share of the vote. Okay, so let's break this question down a little bit more. And let's say that there's two things in here that we're interested in. One of them is that given a certain amount of income, given a certain median income level, what share of votes did Trump win on average? So on average, if a county has an income of $75,000, if a county has a median income of $75,000, what should we expect its support for Donald Trump to look like? Right? You could also think about like, if a county has a median income of $25,000, what should we think that on average, how much did it vote for Donald Trump? What was its share of support for Donald Trump? And so this is conditional because we're saying that like, we're not saying, this is kind of like a group by statement in a way. We're not just interested in what share of votes did Trump win, but we're saying given a certain level of income, conditional on a certain level of income, what was Trump's average support? And so another thing we might be interested in here is, how does this change? So let's say county income changes. How can we expect support for Trump to change on average? Right? So let's say a county's income increases by $25,000. What should we expect to be the change in that county's support for Donald Trump? Does that make sense? So we're interested in both this conditional average as well as how that value is going to change over different levels of income. Okay, and linear regression is going to be one way to answer these questions. And as I said, it's going to be a way of characterizing how changes in one variable, in this case, changes in median income, correlate with changes in another variable. In this case, Trump's share of a county's vote in 2016. And again, correlation is not causation. We're really just interested here. We're just really measuring averages. And we're not going to be able to say anything about what's the effect of income on support for Donald Trump. And we can say, we're going to be able to say more about like why that is a little fuzzy as we go. Okay. Questions so far? How are we doing? Thumbs up? Okay.
Would it be good to use the linear regression when the spread is so big?
What do you mean when the spread is so big? Yeah. So yes, so that's a good question. So right now we're thinking where we're going is we're going to characterize this as a line. You could also think about characterizing this as a non-linear relationship, maybe something like this. That we're not going to talk about today, but it's an important thing to be thinking about. The assumption that a relationship can be characterized as a line is a big one, and it's a one that you should be skeptical of. Okay, so let's just start by thinking more about conditional averages. So given that a county has a certain amount of income, what is its share on average of support for Donald Trump? Okay, so here is just like maybe the simplest way you could think about characterizing that relationship. So here I have binned the data into two bins. So all the counties with a median income of less than $75,000 and all the counties with a median income above $75,000. And this red line represents the average, Trump's average share of a county's vote within each of these bins, right? So this is one way of like kind of very bluntly characterizing this relationship. We're saying that like, okay, we have, here are two like conditional averages, and it's higher, right, over here than it is over here. But this is also like, obviously like is missing a lot of what's going on here, right? Like it's not like this trend is just constant, like over here, we see this like decrease a little bit. And there's probably like a better way that we could do this. So we could split these up into even more bins. And this is a bit more precise, right? We're kind of being a bit more accurate about like, okay, on average, if a county has an income above $100,000, like its share of its support for Donald Trump is going to be pretty low, like versus one with like a kind of an average median income. Those counties are going to be pretty supportive of Donald Trump. So we're kind of like getting a more precise like description of what's going on. We see that like we kind of have this decreasing trend where like more wealthier counties are going to be more supportive of Hillary Clinton, and more and less wealthy counties are going to be more supportive of Donald Trump, which is kind of what we're after. We're after characterizing this relationship. But we could also keep going, right? We could draw even fewer bins or even more bins here. So there's going to be fewer and fewer counties in each of these. And now this is getting, there's a trade-off here. We're seeing that we're picking up more of the variation here. We're picking up this decrease here. These are probably counties, I'm going to guess these are a lot of Native American reservations in South Dakota, Native American reservations in North Dakota, pretty liberal, very poor parts of the country. And so we like, that's interesting, right? But we missed that when we just did the bigger groups, right? So like, that's cool. We could do this again though, right? And we could keep doing that forever, right? So there's a trade-off. That's pretty, on the surface, like that's very ad hoc, right? That is characterizing those conditional averages. It's kind of giving us a sense of how they're changing, but it's also like, it's tough to kind of like summarize that relationship succinctly. And it's also on the one hand, it kind of lets you see those interesting cases, like those very liberal poor counties. But also it's kind of like, it's really sensitive to those values too. And so we see these big swings. So let's take a step back and impose a constraint on how we're thinking about this relationship between income and support for Trump. And we're going to assume, and this is a big assumption, that the relationship between the two is linear. All that means is that it can be characterized by a straight line. There's actually, that has like important like real world implications, but just in terms of like visually, it just means that we want to draw the conditional average as one straight line through the data, rather than a bunch of like little things. Roller coaster. So here is a way of doing that. So this is a way of characterizing the relationship between median county income and Trump's share of the county vote in a linear way. So this is saying that on average, if a county's median income is $25,000, its support for Donald Trump is going to be 65%. And remember, that's an average. It's a noisy average, right? It's a noisy average, but that's the average. You can also say that, like, okay, on average, if a county's median income is $100,000, its share or its support for Donald Trump is going to be like 50%. Okay, so this is really nice because it's very succinct. It's very succinct as a way of describing the conditional averages. And it's also gives us a way of thinking about how this relationship is changing across different amounts of income, right? We can think of the slope of this line, the rise over run, as characterizing how increasing county income correlates with share of support for Donald Trump. So that line is the linear regression line. And as I said, it characterizes the conditional average as a linear relationship. So a natural question is like, where did that line come from? You can draw an infinite number of straight lines, right, through this data. And as Daniel pointed out, this is not a case where I don't know, if you gave me this scatter plot and told me to draw a line through it, that's the best way of characterizing the conditional average. I don't think I would have done this. I think mine would have probably been more like this. Yeah. There are data sets, and actually later on, I'd like manipulate this data set to where it's a lot clearer to show something else. But in this case, it's like not exactly clear, right? And so how do we know that this line is the best line? And what do I even mean when I say it's the best line? So this line, so this is a bit of a mouthful. This linear regression line is the line that minimizes the sum of squared residuals. So there's like 5 buzzwords in there. So we're going to walk through those. Residuals, the first buzzword here, are the remaining errors between each dot and the blue line. And I'm going to visualize this in a second. And this is OLS, ordinary least squares regression. So here's why this line is where it is. Basically, what we are doing is, you could think about, pretend the lines aren't here, and you come up here and you draw a line. From there, you take every single point, I think there's like 3,100, and you calculate the distance between the dot and the line, which is in green. That's what is called the residual. It's the remaining gap between our predicted value in blue and the actual value. So you come up here, you draw a line, you calculate all these lines, and you figure out how long they all are. And this line is the line that if you kept doing that forever, has the shortest distance. If you line up all of these green lines and you put them end on end, there is no other blue line that could lead to a smaller, shorter green line. This line minimizes the length of the residuals. So the reason why it's more of a mouthful and it says the sum of squared residuals is because mathematically this residual is negative, but you don't really want, then they're going to cancel each other out kind of when you try to like stack them end on end. And so what you're going to do is you're going to square them all so they're all positive, and then you're going to stack them on it. But don't worry about that. When you just visualize it, it's just the length of these green lines. So there are 3,100 different green lines here. Some of them might be 0 because this blue line cuts right through the line, right? Like this dot has a super short little green line. This one has a pretty long one. And if you take these green lines and you put this one here and this one here, and you kept going, this is the blue line that minimizes that distance of those green lines. It minimizes the sum of the squared residuals.
Don't you have to square them?
Yes, so mathematically you have to square it. But when you're just looking at the green lines, you can just think about adding them up.
Wouldn't that be absolute value then?
The reason it's squared and not absolute value is because it makes the calculus work better under the hood.
For like the dot, like the spatial.
Yes, for this, I am literally just saying, take this green line, it's this long, put it on the table, take this green line, stick it on top of it, this green line, stick it on top of it. I'm literally just thinking about like lining these all up. So there's no absolute values, there's no squaring, we are just lining up lines. But under the hood, you have to square them because this is technically a negative residual. This is a positive residual, but you want them to mean the same thing. And it's squared rather than absolute value because it just makes the math work. Derivatives of a squared term is a lot easier than a derivative of an absolute value.
Oh, yeah.
So this line is called the line of best fit, and it's the line of best fit because, again, it minimizes these residuals. Okay, other questions out there? Okay. Okay, so I'm skipping over how to calculate this. You will find this in every single like statistics textbook there is. It's on the internet if you want to Google it. There are various different levels of complexity for like what this looks like. I like this book. You don't have to look at any of this, but just in case you're curious. It used to be, we have R to do all the math for us. But it used to be that like 60 years ago, like there were people like doing all this stuff by hand. And it's really insane when you do even just a very, like in grad classes, like you have to do like very small dummy examples of this by hand. And then you realize just like the sheer amount of work that their grad students, not them, but their grad students had to do to like do like very basic quantitative tasks like 60, 70 years ago. Okay, so we've kind of answered our question, like an initial question. Like we have somewhat characterized how Trump support varies with county income, right? But there's other things here that we could add on to this to like give ourselves an even better answer. One of them is like, how could we more succinctly summarize this relationship? Right now, we kind of have a line, and that line is negative, suggesting that as county income increases, Trump's share of the vote decreases, right? But like, we could be a bit more formal about like what exactly that blue line is telling us. So that's one thing. The other thing is how confident are we in what this blue line is telling us? And this one's kind of tricky, but we're gonna talk about this one next, I think. Oh no, wait, we're gonna talk about summarizing first. Okay, so we can summarize the relationship that blue line is telling us by looking at the slope of that blue line. So if you remember from high school, we're talking about rise over run here. This is straight up rise over run. And let's just call that slope, we're just going to give it the name beta. And so that's the slope of our regression line. It's how much it's increasing or decreasing. In our case, it's decreasing. And in words, what it's telling us is it's characterizing the average change in Trump's share of the vote, given a 1 unit change in county median income. And units here is just $1, right? So what our beta is going to tell us is, let's say county income changes by $1. On average, how much do we see Trump's share of the vote decreasing as the county income increases by just $1? And as you might expect, that number is super, super small. That number is super, super small. But that's also because our unit is $1, right? So this doesn't seem like much of anything. But remember, like, again, our units right now are $1. So it gets a lot more realistic if we change our unit from $1 to $10,000. So this is a bit more real world, and this is saying, so now if we multiply by 10,000, our beta becomes minus 0.0, let's just say minus 0.03, which is saying that on average, if you increase county income by $10,000, Trump's share of the vote decreases by 3%, right? And the key thing about this is that it's linear, which means that that is saying that if you change county income from $100,000 to $110,000, or from $20,000 to $30,000, the average change in Trump's share of the vote is going to be 3%. That is a massive, massive, massive assumption that, as Daniel pointed out at the beginning, like oftentimes might not hold, right? So today we are making that assumption because it simplifies our lives and it's the place to start, but be skeptical of it. Okay, so here is like the rise over run visualized. So here we have a change of $10,000. We're moving from, what is that, like $75,000 to $85,000. And then you see in orange right here, that is the resulting change in support for Trump when you increase $10,000. So it's negative, which means our line is decreasing, and then the magnitude is going to be captured by 2.52. Okay. How are we doing? Good, okay. Okay, so now we've kind of summarized our relationship, right? Like our question at the beginning was, what was the relationship between a county's median income and support for Donald Trump in the 2016 election? Like we have kind of an answer to that right now, right? We say that like, on average, as counties, on average, counties that are more wealthy, that are technically have higher incomes, support Donald Trump less. We know that because our slope of our regression line is negative. And we can also say something about how much of a change is happening. It's a decrease of 2.5%. But now we need to think about how confident we are in this relationship. How much do we really think that 2.52 number is telling us something real and isn't just like kind of not really much, it's kind of much ado about nothing, okay? That's going to be a lot clearer, hopefully, when I visualize it. So I really like this plot. So this is completely fake data that you should never, ever, 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 ever do this. But this, let's imagine this was the relationship between county income and Trump's share of the vote. All I've done is I've taken those green lines, those residuals, and I've shrunk them.
Oh my God.
Okay? And if you saw this, so a way of thinking about this, when you're thinking about how confident you are, remember when we said like, I don't really know where to draw that line? If I gave you this data, you would be like pretty good at drawing that line, right? Like it's pretty clear where that line of best fit falls, right? We'd be more confident that this is actually the slope here of this line. So a crucial thing, this took me so long to really grasp, was confidence and magnitude are completely different things. The slope of this blue line, is the exact same as the slope of this blue line, right? This line has a slope of minus 2.5, as does this fake data one. They have the exact same slope. It's just about how much we think, how confident we are that that is actually the real slope. Does that make sense? So confidence, you can have a really large, a really steep line through some data. And that in no way means inherently that it's a better result, a result that you can be more confident in. It might be a more interesting result because it has more of a substantive impact, but you could have a steep slope where there's a lot of variation in it. And you could also have you could have that same thing where all the residuals are shrunk and you're more confident. So confidence, how confident you are in your findings, and magnitude, the magnitude of the slope, are two different things. Okay. So another way of thinking about this is that compared to the real data, we're more confident here. We're more confident that the real value of beta is right around where we estimated it.
Is confidence like a calculated thing? Because like magnitude being like the slope, but you're small of it. Is confidence just like visually, it seems like this, or is that something that you actually calculate?
It is. So if you see where we're going is like p-values, confidence intervals,
Okay.
that's like the mathematical way that you're gonna see this. Yep. So, yeah, and this is actually where we are right now. So we can formalize what we're doing right now by thinking about setting a confidence interval around beta. So what does that mean? So this is how we're going to try to think about how we could get a confidence interval. So this is tricky. And it's tricky in large part because a lot of statistics was created from a survey from people who wanted to learn stuff from surveys, largely from these ISR folks, like literally 2 blocks away. And so some of this is a little tricky to think about when you aren't working with survey data. But imagine that I have a big bag and I have all of my counties in my big bag. And what I'm going to do is I think there's 3,100, let's just say there's 3,100 counties. I'm going to put all my 3,100 counties in my big bag, and I'm going to draw out 3,100 counties, and I'm going to calculate the slope. But I'm going to do that. Once I pull a county out, I'm going to put it back in. So I'm not going to be pulling out the same data set every time, because I could pull out Washtenaw County twice. I could pull out, oh my God, now I'm like totally blanking on a county that's not Washtenaw. What county is Detroit in? I could pull out Wayne County 5 times, right? I could pull out Washtenaw County 0 times. So imagine I have this big bag. I'm pulling out these counties. I pull them out, I put them back in, and I do that 3,100 times, and then I calculate my regression line. Okay? And then I do the whole thing over again. And I keep doing that. So each time that I pull out 3,100 counties from my big bag, that's a new sample of data, and we could recalculate beta and see how much it varies from one sample to the other sample. So let's do this. So this is the real data. The blue line is the line of best fit with the full actual data set. These other lines are, I've taken all these counties, I've put them in my big bag, pulled it out 3,100 times with replacement, and I calculated the regression line, and the regression line was this one in green. And it's different, again, because maybe I don't pull out Washtenaw County that time. Maybe I pull out some more conservative counties more, etc. All random, but that's just random chance, right? And in this case, I did this like 5 or 6 times. If you're doing this in the real world, you do it 5,000 times. But that's what computers are for. So this is kind of giving us a sense of like how much our value of beta, what this is kind of capturing is we have a lot of variation in our data, right? There's some, like at a point here, there's some counties that really supported Trump. There's some counties that really did not support Trump. And when we do this, we're kind of capturing, we're kind of formalizing, capturing the fact that like that makes our estimate of beta a bit more messy. It makes it a bit less precise. And
Are we taking out one every time?
taking out one.
Taking out any from the data set?
No, so we are not taking one out. We are resampling. So everything's in my bag, and we're pulling out the same number of counties every time.
Okay.
3,100.
Okay.
And then
How do you set the number in proportion to the?
how do we?
Decide the number.
Oh, the 3,100 number. The 3,100 number is the number actual number of counties in the data set. So this is not, I think you're thinking of like the take one out validation stuff, right? Kind of. Okay, well, we have our data set. There are 3,100 counties in the United States. We're resampling that same number, 3,100. The difference is that we're sampling with replacement. We're pulling out a county and we're putting it back in. And so here's kind of the key thing, is that we see a bit of noise here. We see a bit of noise here in our value of beta, in our magnitude of our slope, right? This red one is a bit more negative. This green one is a bit less negative, right? But there's like some gaps here, right? These slopes are different. Maybe they're not that much different, but they are different. And perhaps most importantly for our purposes here, they're much more different than this case. In this case, when we resample, when we put all our counties in our bag and we resample them, all the data is pretty darn close together. And so this resampling with replacement isn't going to lead to data sets that are very different from one another. And therefore, it's not going to lead to regression lines that are all that different from one another either. So that's why in this case, our value of beta is pretty tight, right? It's pretty, across these repeated samples, it's remaining pretty darn close to minus 2.52. So if you saw a confidence interval, and so usually, actually it should be always, if you saw somebody say that the slope of the regression line, where you're regressing Trump's share of the vote against median county income, and that value is minus 2.52, they should always be telling you some information about how confident they are in that relationship. And so that can be expressed with a confidence interval. And so maybe the confidence interval is from -3 to -2. And let's say that confidence interval is at 95%. That means that if we did this bag resampling thing 100 times, 95 times, we would get a value of beta between -2 and -3. 5 times, we would get one that would be above or below that value. And so maybe that's our confidence interval in our real data. Maybe in our fake data, it's -2.6 to -2.4. That means that if we did our bag thing 95 times, 95 times we would get a value of beta between -2.4 and -2.6. It's tighter. That's the key thing, is that we're more confident that that value of beta is within a small area. Another thing, Eleanor, I think you brought these up a few meetings ago, is another thing that you often see as a way of expressing confidence in an estimate is a p-value. And a p-value is telling us, let's go with our slope of -2.52. Let's say that the real actual in reality, the slope of beta is 0. Our slope of beta is 0. Our p-value is telling us how likely we are to observe a value of -2.52, given that in reality, the value of beta is 0. So that's why low p-values indicate higher confidence. Because if you have a really low p-value, that's saying that the likelihood that your result is due to random chance and it's actually 0 is super low. So again, and this is also like, I've kind of skipped over this, and this would be, if you're tripped up on this, it'd be very understandable, because I think I am also would share in this confusion. I keep saying this like truth kind of thing. It makes a lot more sense in a survey setting, where like, let's say I survey 1,000 people, and or let's say it's 10,000 people, and it's a nationally representative survey. I have my survey values, but then there's also this theoretical unknowable value. Let's say we're surveying support for Donald Trump. I survey 10,000 people, and they tell me that on average they support, like, the 54% of people support Donald Trump. That's my survey value. But then there's also this unknowable value that I'm actually interested in, which is like, what's that value in the real population? So that's like the survey setting of like what the truth is. It's tougher here because we're not dealing with survey stuff. So it's really about like how noisy our data is, kind of. Okay, so just a few more things. Let's take what we've talked about so far visually and apply it to what you're usually going to see, which is a regression table. So here is the same thing that we've been doing, just expressed as a table. So let's walk through this. So our dependent variable is the percent of votes won by Trump in a county. We're interested in the relationship between this and, in our case, just one independent variable, which is median county income. There are, I was close, 3,114 counties in the United States. Here is our slope of beta. On average, as median county income increases by $10,000, Trump's percent of votes in a county decreases by 2.5%. The constant here is, we're doing a throwback to math class here from high school, but this line right here is slope intercept form. Y equals, you guys probably can't see this. Y equals mx plus b. This is our beta. This is share of vote. This is median income. And as you might remember, and it's totally okay if you don't, when you have this slope intercept form, you also have this beta, which is telling you, so this right here, y equals mx, is just telling you like how steep of a line are you drawing through the point 0, 0. But if you want that the line to go through like further up on the y-axis or further down, that's going to be changed by this value of beta. And this value of beta is the constant. So sometimes your value of the constant in a regression is going to mean something like substantively. It always has to exist because that's how you draw a line. But like sometimes it has a substantive meaning and other times it doesn't. This is a case where it really doesn't, because it's saying on average, if a county had a median county income of $0, its share of support for Donald Trump would be 75%, right? And so that doesn't make sense because there are no counties where that's the case. Like we would be really extrapolating way too far. And that's also one where it's just nonsense because that just doesn't make sense. In other cases, though, you totally could have a value where like you zero out your independent variable and a value of 0 actually makes sense. One of those cases would be, let's say this variable here was equal to 1 if somebody's sex was male and 0 if it was a female. This constant term would tell us the average support for Donald Trump. Oh, wait. Sorry. That's at the individual level, not the county level. Let's say it's, okay, is the county in the South or not? It's equal to 1 if the county's in the South, it's 0 if it's not. This value is telling us the average support for Donald Trump in counties that are not in the South. This beta term is telling us the difference in support for Donald Trump in counties that are not in the South versus counties in the South. That increase, the change. So that's a case where the constant term has a real meaning. Okay, so next thing here is we haven't talked about confidence yet with the table. That is also being expressed here. The 3 stars are saying that the p-value is less than 0.01, which between in words, that means that if the real relationship between median county income and support for Trump was 0, there was no relationship between a county's median income and the percent of votes won by Trump in a county. If that was actually the real case, we would see this value pop up by random chance less than 1% of the time. So we can be pretty confident in this. The standard level of statistical significance is 0.05, which is completely a made up number that somebody at one point said that's statistical significance. It's totally made up. This value under here is a standard error, which you need to calculate a p-value. Other interesting things here. This is saying on average, the residual standard error is saying, let's see if I can get this right. On average, the length of a green line is 15 percentage points. Percentage points because that's the unit of our y-axis. So on average, the difference between our blue line and our dot is 15 percentage points. R squared is giving you, we usually don't care about this. This is saying how much of our variation in county support for Trump is explained by the variation in median income. Adjusted R squared is because as you add more variables here, which we're going to talk about in a second, this R squared is inherently going to go up. Adjusted R squared controls for that. F statistic only. We usually aren't interested in R squared. You care a lot more about R squared if you're Amazon and you're trying to predict what somebody wants to buy, then you're really interested in making sure that you fully explain people's buying habits. But we're interested, we're usually not interested in R squared. Okay, last thing. Everything so far has been a bivariate regression. We've had our dependent variable, and then we've had one independent variable, right? And that independent variable is median county income. But if you're interested in this, in like actually doing something like this, a very like one of the first things you might think about is like, there's a lot of other things that probably explain counties' support for Donald Trump other than their income, right? One of like the one that really jumps out to me is like race. So we might also want to include those values, kind of control for those values when we are doing these regressions. So I just want to talk about that really briefly. So here is the same regression table, except I've added this variable that is the percentage of the county that is white. So what has happened? We see now that on average, as you increase median county income, we see more of a decrease in percent of votes won by Trump in the county. This is saying that holding constant the racial composition, or specifically the share of whites in a county, setting that to a specific value, not letting it vary. As you change median county income, it decreases by almost 4 percentage points. Another way of doing this is like, if you set median county income to a certain level, you hold it constant, you don't let it change, and then you increase the share, the percent of whites in the county by 1 percentage point. That leads to a 0.5 percentage point increase in percent of votes won by Trump. Last thing here. So why have we done all of this in bivariate? Because you can visualize it. As I'm going to show you in a second, when you have two independent variables, rather than drawing a line through your data, you're drawing a plane through the data. And then once you get to 3 independent variables, you're working in 4-dimensional space. And so you just can't visualize it anymore. So usually this stuff isn't you can't visualize it, right? It's the same intuition, but it's just outside of like what we can comprehend. So let me show you. So this is what it looks like, but it looks really crummy in the plot. So here, okay. So this is so just don't look at the plane for a second, even though it's like kind of hard not to, but like just focus on the dots. This is the same thing we've been plotting so far right now, right? We see this relationship where we have median county income. Now it's in tens of thousands of dollars on the x-axis, and we have Trump share the vote on the y-axis. So that's what we've looked at so far. You could also run another bivariate regression. Again, don't look at, just pretend the plane's not there. Here, this is what the bivariate regression would look like if you replaced median county income with the share of county that is white. And this shows that this one's starker, I think, than the median county income, where you have really white counties on average support Trump more, and then that decreases as the share of the county that's white decreases as well. But what we've done is we've plotted these in 3-dimensional space. So each one of these points is calculating. So this is calculating, this is like, this is a county. That county has, let's say, a median income of $60,000 and it's like 60% white, and it supports Trump 75% of the time. What we've done with this regression line is now it's become a regression plane to try to now we're thinking of the plane of best fit. It's the same thing though. It's the same thing. We could draw little green lines little green lines from each of these dots to the surface of this plane. And this is the plane that minimizes the distance of those green lines. It's the same thing, except now it's a plane rather than a line. But you could think about it, so like, okay, so that means like, so it's characterizing, it's doing the same thing where it's characterizing the conditional average. I'm trying to find a good angle to visualize that. You see that the average is decreasing in, let's see if I can get this right. So this is sloped down like this. Remember that our slopes on both the share of county that is white and median county are negative. And so this is saying that, like, let's say we hold median county income at $80,000. That's going to put us someplace on this plane. And then our slope of minus 0.52 for percent that's white is saying that it's going to, at that point, as if we move this way, it's going to decrease. The share of the support for Trump is going to decrease. Holding constant median income at $80,000, our predicted value for support for Trump as we change the share of county that is white is going to decrease. Okay. Perfect time. Oh my gosh. Okay. Other questions out there?
Can you make these plots in GG plot?
You cannot. I spent a frustrating amount of my afternoon making this one. I had done everything. All of this was for a class that I GSI'd a couple of years ago, Poli-Sci 381, which is the class you take as a junior if you want to write an honors thesis as a senior. It's a really good class. But I didn't do this. And so I tried to do this afternoon. And this is with another package called Plotly, which is in R, it's also in Python. I found it infuriating, but it did happen. It did work, kind of. So yeah, there's very one of my pet peeves is like Excel charts that are in 3D for no reason. And there's actually a reason for this one to be in 3D, but usually you don't need 3 dimensions. All right, I'm going to stop sharing. Stop recording.